Good afternoon, everyone. My name is Thomas Abraham, and I work at Arm and primarily focus on developing platform software for Arm's system guidance for infrastructure reference platforms. This talk is about enabling a RAS on ARM-based server platforms, and there's quite a lot of work that we have done on enabling RAS error injection and error handling on the SGI-575 platform, and some of the lessons learned from that is part of this talk, and we'll also see what are the current upstream status of the various components that are required to implement a complete RAS error flow. And what are the platform, the reference support that we have implemented on SGI-575. For implementation of a complete RAS error handling flow, there are multiple components that are actually required. There are many ways in which the RAS error flow can be implemented. Primarily for the ones that require firmware-first handling, there is an interaction between the firmware and the Linux kernel that is actually required to complete the error handling. So some of the components that have been used for implementation of this RAS include the Secure Partition Manager, the StandaloneMM APEI Dixie driver, the SDI dispatcher, SDI client, and things like that. So quite a lot of components have been put together to enable a complete end-to-end RAS error handling. And as I mentioned, so this has been tested on the SGI-575 FVP platform, and some of the lessons learned from that has also been shared in this talk. Talking about specifically about the components that are used in the RAS error flow, the first one would be the Secure Partition Manager. This is a component which is part of the ARM trusted firmware, and this primarily acts as a gateway between the non-secure software and the secure partition, which we are using, which we currently are using, which we are using a StandaloneMM for that as a secure partition for the RAS use case. So any communication that has to happen between the non-secure world and the StandaloneMM is the secure partition manager acts like a transit for that. The other component is the StandaloneMM. So this is the secure partition which is sandboxed by the secure partition manager. The StandaloneMM implements RAS error injection and error handling drivers, and it also supports reporting back the platform errors that are supported, and the generation of the CPER error records as well. The third one would be the SDI dispatcher, and the corresponding the part of that is the SDI client as well. The SDI dispatcher and the SDI client are required for passing on certain information about the events that the firmware has actually captured, and SDI dispatcher notifies the SDI client, which is the Linux, which is part of the Linux kernel, about a particular system event that has occurred, and it uses, and these two components, the SDI dispatcher and the client, work together to pass on the system events from the firmware to the Linux kernel. The other component is the APEI Dixie driver. This is part of the StandaloneMM, in fact, and the APEI Dixie driver helps the platform to query the different error sources that are implemented on the platform. So the error sources are information about the error sources are securely stored in the secure EL0 mode, which is a StandaloneMM execution environment, and the non-secure code which is executing in UEFI uses the APEI Dixie driver to query the error sources that are available on a platform. For instance, the error sources could be an platform error coming out of a memory controller based on some errors that it has found. There could be the CPU itself could be one of the error sources, or the cluster itself, or the interconnect. So there could be multiple components which could be generating the RAS events, and the APEI Dixie driver is responsible for getting the list of those errors supported on the platform. So these components are primarily used for handling of RAS, which require firmware-first handling. Those that can be directly handled by the Linux kernel itself, so this would not be the flow. But in cases where certain events which need to be handled in the firmware, so we would require these components to be used. So there are three primary things in enabling the RAS functionality. One would be to during the boot phase, populating the HES table with the error records. The second would be so that is during the boot phase. There's a one-time thing that happens. The second part would be the error injection itself. Getting a RAS error on a real system would be the probability of getting a actual RAS error is rather very low. So we need a mechanism to validate the RAS error handling functionality. So error injection helps induce errors into the platform and see how the platform behaves. The third one is in fact the actual RAS error handling flow itself. The three main aspects of this. So I'll just quickly go through those aspects. The first one is the preparation of the HEST ACPI table. Now, HEST ACPI table contains the list of error sources that are supported on a platform. So, the platform code uses the APEI Dixie driver to talk to the StandaloneMM code, the software executing StandaloneMM code, to find out the error sources. Now, it can't directly. This is executing in the EL2, and this is in secure EL0. So it uses the secure partition manager as a transit, and it uses something called as the MM communicate protocol to actually talk to the standalone MM. There is a corresponding API SMM driver implemented on the standalone side that talks to multiple SMM RAS drivers that are implemented in StandaloneMM. Now these SMM, so now for each of the error sources that are implemented on a platform, there is a SMM driver for handling that particular error. For instance, if there's a DMC error, there will be a driver that handles errors from the DMC. There could be one that handles errors from the CPU, and there could be one that handles from the, let's say, an interconnect. So the first step in establishing the RAS error flow would be for the platform software to query the StandaloneMM implementation to find out the error sources that are available on a platform. Now, having retrieved that through the secure partition manager, the APEI Dixie driver then populates the ACPI HEST table. And then the next stage would be to boot to the Linux kernel. Now the Linux kernel looks at the HEST table and identifies a list of errors that are available on the platform. So that's about the HEST ACPI table, populating the errors into the HEST ACPI table. The next step would be the error injection. Now, having the system booted into the Linux kernel, the next step would be to see if you can actually inject an error and get back an error record from the firmware. Now, the standard mechanism of doing that on an x86 platform is to use error injection table, and the support for using error injection table and injecting an error is part of the upstream kernel also. But on the ARM platform, there are cases where the registers which the Linux kernel needs to access is behind a secure access. So in which case it's not possible to use an EINJ table as of now. So we still have to work on that. But for the purposes of validating this flow, the other mechanism that which has been implemented on the SGI-575 platform is to use an SMC call and get into the SMC, the secure partition manager. The SMC call initiates an MM communicate into the standalone MM. The standalone MM would then correspondingly invoke one of the error drivers and request that particular driver to inject an error. Now, if, for instance, if we have to inject an error into the DMC, into the memory controller, the SMC would request that with an indication that the requested injection is for the DMC error event, in which case the driver handling the DMC errors would be invoked, and that would be requested to inject an error into the DMC. So that would cause an error to be generated, a platform error to be generated. So that's a non-standard way of implementing errors. But one of the next things to do is to use find out some ways of using the standard ACPI error injection methods. So that's about populating the HES table and the error sources and also using the error injection. Now the error handling part in itself, this shows the complete error flow, error handling flow. So just quickly going through this, the error is initially the RAS error interrupt is picked up by the platform RAS error handler, and then there are two main processing phases that it goes through. The first would be so the error is picked up by the platform error handler, and the first stage would be to use MM communicate and get the RAS error driver that is implemented in StandaloneMM to service that particular interrupt, and then generate a CPER record using the CPER library. Now all of these drive, so on RAS error interrupt, the interrupt number that actually caused the RAS error is notified into the SMM event handler. The event handler then knows which one of these has registered to that event, and it invokes that SMM driver, which in turn handles the source of the error and then generates a CPER record to notify the Linux kernel about the actual error that has occurred. This is a CPER library, generation library, which is part of StandaloneMM, and all of these drivers can actually use this library to in fact generate the CPER record. And the CPER, the memory for the CPER record, it could be, it's again depends on how the platform implements it. There could be a static allocation for the CPER record, or it could use a dynamic allocation as well. So those are some of the platform considerations that come into picture when we talk about the CPER generation. And after having so this phase, the first phase is about identifying the source of the error and generating a CPER error record for that. The next phase is to use the SDEI dispatcher to let the Linux kernel know about a RAS error event that has occurred. Now the SDEI dispatcher just dispatches one. So for each of the RAS error event, there is an SDEI event number assigned to it. These are all the platform specific changes that we have to do. And the SDEI dispatcher, based on the RAS event that has occurred, dispatches the SDEI event into the SDEI client. And the SDEI, and there could be consumers of that SDEI client event, which would register with the SDEI client to get notifications of one. So quickly going into the details of the complete error flow, which the two main phases that we talked about. The first phase, the errors are routed into the exception handling framework, the EHF framework in ARM trusted firmware. The RAS module in ARM trusted firmware picks up the handling of the RAS interrupts. It then forwards the handling into a platform RAS error interrupt handler, which then uses the secure partition manager to reach to the StandaloneMM. Primary thing to note here is that all the RAS error events, RAS error interrupts are grouped routed through group 0, which end up as a FIQ interrupt on the core, and those interrupts are then taken up by the EHF and then routed through the secure partition manager. From there, the secure partition manager is used to using the MM communicate, the actual source of the error is notified to the SMM event handler. The SMM event handler then picks up one of these drivers to handle the RAS error. So it looks at the source of the error, the reason for the errors, clears any particular condition on that particular peripheral to clear the source of the interrupt, and then it goes ahead and uses the CPER generation library to generate a CPER error record. Now, the CPER error record is a memory allocated by the platform software, the platform code, and it could be a statically allocated buffer or a dynamically allocated buffer, depending on the choice of the platform. Now, this CPER record is actually is in fact tied into the HEST table. So the HEST table has multiple GHES error records, and this for each of these error record there would be a CPER buffer that would indicate what the error is. So that's the first part of the handling, where the error record has been now noted down in a CPER record and which is attached to the HEST table. Moving on to the second stage, so the next stage is, so for each of the RAS errors, so there is an SDEI event that is allocated to the RAS event. So that's again a part of the platform port that has to be implemented. Now, based on the RAS error, the platform handler uses the SDEI number, which is platform specific, and passes it on to the SDI dispatcher. The SDI dispatcher then talks to the SDI client to notify that a particular SDI event has occurred, which could be basically a RAS error event. The SDI client then receives the event notification, and in cases of a RAS error event, the GHES driver would have so during the boot phase in the Linux kernel, the GHES driver would have subscribed to SDI client for notifications about the RAS error events. So in case the SDI client receives a RAS error event, so it's forwarded into the GHES driver. The implementation that we have currently done is the GHES driver just prints out the CPER error record contents onto the console. There could be further processing on based on the error type, like for instance, if it's a correctable error or a non-correctable error, there could be further actions which could be taken by the GHES driver, but that's something that we have not looked at. And also reporting that error into the user space using something like a Redfish API or something like that. So that's something that we are yet to look at. So the delegation by the dispatcher into the SDI client and then finally notifying the GHES driver about a RAS event completes the entire flow of the RAS error notification. So after the CPER error record is consumed, the acknowledgement is sent back to the StandaloneMM saying that CPER record has been looked at, and it can be, if it is a dynamically allocated buffer, that buffer can be subsequently freed. So that's about the HEST table preparation, the error injection, and the error handling mechanisms that we have used on the ARM's system guidance for infrastructure platform. So this is primarily targeted at errors that have to be handled in the firmware-first mode. And the current status of this particular implementation is the secure partition manager and the SDI dispatchers is already upstream in trusted firmware. As an example of a platform that implements this error flow, the SGI-575 implementation in ARM trusted firmware is upstream, and wherein it actually can handle errors and then use as an MM communicate to talk to StandaloneMM to create CPER records. and then pass it on to the SDI dispatcher and the SDI client to handle the particular platform error. There is some amount of work to be still done on enabling the StandaloneMM package, StandaloneMM patches in EDK2, and it's currently we are looking at this. Progress has been slow, but still working on this. There's also a few bits on SDI client and the GHES driver which have to be still upstreamed in the Linux kernel. So overall, the RAS error handling mechanism has been in development on SGI-575 platform. There's a lot of focus on getting this upstream so that other ARM platforms which would be interested in implementing a firmware-first error handling solution can probably the SGI-575 platform can probably act as a reference platform for that. Yeah, that's it. I mean, that's what I wanted to talk about in today's talk. If there's any questions, let me know.
Sure. Thanks, Thomas. Any questions? No? All right, Thomas. Thank you so much for your presentation.